section 24, vibration of molecules. And well, we have to first of all admit that we couldn't figure out how to prove that the condition corresponding to constant angular momentum should give me a constraint on the displacements to be this equation being equal to 0 as opposed to being a constant. Okay, so we tried and we failed. And well, let me just say that we tried to find a constraint finally, and the constraint seemed to depend on UA, which is not possible because we only added constants. If you don't understand, it doesn't matter. It didn't help anyway. Okay, so let me start with what was more interesting. We look at some very simple symmetry and group theory arguments to arrive at useful results. Well, useful, so to speak. N atoms is what we consider first of a molecule which is in a plane. Okay, so for a molecule which is in a plane, there are 2n degrees of freedom, which is okay. Yeah, so there are 2n degrees of freedom because you can't move anywhere else. So there's 1 and 2, and there are n of these, so 2n. And of these, there are 2 translational and 1 rotation. So this is the total. So total, it can go forward, backward. No, hold on. Of these, there are 2 translation and 1 rotation. Kichu, I got confused. So 2 translations and 1 rotation. Okay, so within the plane, so the plane itself has 2 translations and 1 rotation degree of freedom. My mistake. So that's as the rigid body. Number of normal mode vibrations that leave the atoms in the plane will therefore be 2n minus 3, where 3 is 2 plus 1. Okay. This tells us that the remaining degrees of freedom will be vibrations which take the atoms out of the plane. And these are 3n minus 6, which is the total number of degrees of freedom, minus the ones which are normal vibrations, which leave the atom in the plane, which is, and the result is n minus 3, which are the vibrations which will vibrate the atom out of place, out of plane. Next, we consider n atoms for a linear molecule. So for a linear molecule, each molecule has only 1 degree of freedom, n atoms. Therefore, the degree of freedom will be n, and the only macroscopic movement you can have is translation. So the degree of freedom left for vibrations will be n minus 1. Now, since the total degree of freedom, remember again, is 3n minus 5 for a linear molecule. The 5 is, remember, because it's a linear molecule, so one of the degrees of rotation doesn't count. Therefore, the difference will give you the degrees of freedom, which will correspond to taking the atom out of line. So n minus 1, let me tell you quickly, is the degrees of freedom which keep the degrees of vibration, which keep the atom inside the plane, inside the line, and these 2n minus 4 are what take it out of the line. Okay? And now there's one interesting remark, which is that these 2n minus 4 do not correspond to 2n minus 4 degrees of freedom. 2n minus 4 frequencies, they correspond to at most n minus 2 different frequencies, because there are 2 mutually perpendicular directions along which the vibration can happen out of the plane. But the point is that because of the symmetry, these 2 should be identical, which means that the frequencies for both of them should be the same. Okay, so that was that. Now let's go on to the damped oscillation section. Now, obviously, what we've done so far looks like was in vacuum, because we did not consider a medium, and we know that in a medium there's usually some sort of retardation, and consequently there is some sort of heat which is produced. So in this case, the motion is no longer purely mechanical, so to speak, and we are forced to use, and we can no longer use just function of coordinates and velocities in our equations, and for forces just a function of coordinates as we did. What we'll do is we'll consider therefore a special class of medium which is approximated in small frequency compared to dissipative forces. So basically the assumption is that your dynamics is smaller compared to the frequency of dissipative processes. Okay, and in this particular assumption, you can model the friction as a function of velocity. So friction is the force which models this dissipation, and that is can be taken as a function of velocity. And if the velocity is small, you can expand the force and powers of these velocities. And it turns out that the 0th order force is to 0th order, the force is 0, because obviously it's not, a block can't start moving by itself. It has to be moving for friction to apply. So friction doesn't act on bodies which are at rest. Therefore, now we want to look at only first order corrections to this force, and which is why we consider F friction to be minus alpha x dot, where x dot is the velocity of the particle, alpha is a positive constant, and the minus sign is written explicitly to tell you that the force, frictional force, is always going to be opposite compared to the direction of velocity. Okay, so now let's quickly write down the equation of motion. So you can write mx double dot minus kx. This was the usual small oscillation term. Now we add minus alpha x dot. Okay, that's the friction term we've added. You normalize them with the mass, and you eventually obtain this equation. X double dot is this. And as usual, you add your answers, which is e power rt, and you would find that once when you solve for r, the quadratic equation gives you two solutions, minus lambda plus minus root lambda square minus omega naught square. Now the general solution therefore can be written as a combination of these two. We first consider the case in which lambda is less than omega naught. In this case, r has two complex conjugate values. So the general solution will be x is equal to real part of lambda t plus I blah blah blah, whatever this is, because it's a part which can be real or imaginary. And a is some arbitrary constant, which is in general left to be complex, so you can add a phase. And so therefore, when you write it, it will be xa e power minus lambda t, which just pops out of the real part, and the a has the real and imaginary part, so that this is the a, the usual one, and the imaginary part goes in here. And you put omega t, and now omega is obviously this square root of this entire term. Okay, and we assume lambda to be less than omega naught, so we know this guy is purely imaginary. Okay. Oh, sorry. This guy is purely lambda is less than omega. So this guy is purely real. So you know that. And so now what you do is what you obtain is a situation in which you have oscillations happening and there is a damping. Okay. And there are two remarks. The rate of, and this is very interesting, the rate of decrease is given by lambda. Okay. So that's okay. But the second one is actually the interesting one, which it says that the frequency omega, which is less than omega naught. Obviously, there is a lambda sitting here. But the interesting part is that if you try to expand this expression for omega around lambda and you assume lambda is small, then you would see as the correction to omega naught is second order in lambda. Okay, so this first term runs away. I mean, it disappears because it's proportional to lambda itself, and you have to put lambda equal to 0 to expand around it. And so you get omega naught corrections. So the corrections to omega, this is the point you want to take home. Corrections to omega will be lambda square order. And so if lambda is small enough, then in that case, you can assume your motion to actually be the amplitude to be, the frequency to be roughly unchanged as the motion happens for the parts that you're interested in. And the consequence, as I said, is the so this period that you're interested in will be 2 pi by omega, and this basically suggests that you can neglect e power minus lambda t while you're taking mean and things like that. And that also has further interesting consequences, which is the fact that using just that, you can estimate how the energy decreases. So energy, is going to be square of the coordinates and square of velocities and so on, and both of these things will be proportional to minus 2 lambda t, you see, because you had e power minus lambda t, you do x square, you get 2 lambda t. Therefore, the energy will have to decrease, and the decrease will be given by E as E naught e power minus 2 lambda t. That's done. Now let's consider the second case in which lambda is greater than equal to omega naught. Well, in this case, you would first of all want to note that this entire object will have to be less than lambda, which means that R1 will have to be negative because minus lambda plus something which is less than lambda. In the other case, both the terms are negative, therefore R2 is also going to be negative. So in either cases, what you are saying is that the general solution will be given by x equal to exponential of something negative and C2 into exponential of something negative, and both of these proportional to time. Now what happens is that this motion basically will decrease to the equilibrium position, which is x equal to 0 asymptotically as t tends to infinity. Okay? And this sort of a motion is called aperiodic damping, and there is no oscillation, therefore the word aperiodic, and that's my guess. Okay, so now the special case is something we have not explored actually in much interesting detail. You just put lambda equal to omega naught, you'll see R1, R2 become minus lambda. Get C1 plus C2 e power minus lambda t. Now I don't know what else to do with it, but that is the idea. Okay, now let's look at a system with more than 1 degree of freedom. Okay, and this I think is the last section for today. Okay, don't get scared, it's really nice. What we do now is we write the generalized form for friction as f of Fri. So generalized meaning you're doing it for many atoms or molecules or particles, whatever. And this is the form that we write: summation k alpha I k x k dot. Because you already know that it has to be negative, but this metric is something which follows from the statistical physics. So we assume alpha I k is alpha ki. Okay, and this Kishore will tell us in the next series.
Okay.
Uh, Yes, and he confirms. So that's good. So we have it. We have him on record. In the meantime, let us get back to this. So thus we can write Fri as a function of I. Sorry. So this coefficient. Sorry, this force of friction we can write as minus capital F del by del xi, and capital F. Then if we write like this, we will get the same alpha ik. Okay. And the nice thing is that this is a quadratic form. And why that is a quadratic form? Well, it just, first of all, it just follows from so if you plug this in, you will get the required condition. And the fact that it's, yeah, so we'll see why it becomes interesting. Okay. So in the meantime, okay, so let's get back to this. The force is added to the RHS of the Lagrangian equation. So we already know this is the usual Euler-Lagrange equation. Now to this, we've added one more term. Now note, we are not adding something to the Lagrangian in itself so that we obtain an Euler-Lagrange with this force. We are adding a term to the Euler-Lagrange equation itself. And this will have some implication. We'll see in a minute. What is the physical significance of the dissipative force? Dissipative function. So first, a word on why we added this. Obviously, on the right hand side in the Euler-Lagrange, you have all the forces. So del by del xi is the usual force coming from the potential, and to this we've added the dissipative function, the derivative of it, which is actually the friction force. Now we want to see what is the physical significance. So first we'll recall the expression for energy in the Euler-Lagrange picture, which is this, that you will have xi dot del L by del xi dot. So there should be a dot chemist minus L. And now what you do is you evaluate the derivative, which is not a big deal. So you'll get xi double dot del by del xi plus xi dot d by dt of this guy, and then minus d by dt of L. Okay. Now d by dt of L you can expand because L is just a function of x and x dot, so you can write it as follows. Now you see this x double dot term in the second. So the second term, the x double dot term, will cancel the first x double dot term because there's a minus sign sitting here. So you'll be left with just two terms, which you can see here, and both of these terms have an xi dot common. So you pull out the xi dot, and you will have these two terms, d by dt of del L, and this other term, you will have these as common. And now you remember your Euler-Lagrange, in fact, was exactly this equation, and to it you added this one extra term, which was minus del F by del xi dot. Now you make the substitution at this stage, and you see, well, obviously the energy is decreasing. Now we use a fancy word for the fact that your f is a quadratic function, and you take a derivative of quadratic function and you multiply it with x. What do you get? Well, 2 times the same function. So this is what we are saying. d by dt is going to be equal to minus 2f. And now we know from our physical understanding that f has to be positive. And this is why he did all of this, is to say that f will have to be positive, because if it was not positive, then the energy would it would increase exponentially, which is not something we want, or which is something which is not physical. Dissipative forces always lead to loss of energy. Now there's an interesting note here that your Lagrangian in all of this, del L by del T is still equal to 0. And even then the energy is not conserved. And this is something I hinted at already, that we are not adding a term to the Lagrangian. Okay, so let me say a few things. We know that in general, if del L by del T is 0, then the force is the energy is conserved. And in this case, we saw that energy explicitly depends on this force F, so it decreases proportional to F. Now, excuse me. Why that actually happened was because we did not add a term to the Lagrangian. We added a term to the Euler-Lagrange equation. Okay. And so that means everything we derived about the dynamics of the system was assuming the Euler-Lagrange equation. And in this case, we're not assuming the Euler-Lagrange equation, we are assuming a modification of it. So that explains that. And so let's put that to good use now quickly. So remember that this was the general form that we had for oscillations in n degrees. Now we want to add friction to it. So friction, as we saw, you can just write as L alpha ik x dot. You put it on the left hand side, and again plug in xk as ak e power rt, sorry, and you will again get an algebraic equation which must have the determinant set to 0 if it is to hold for all ak. And now this is an equation in R with degree 2s. So that basically means that R square, I mean, so basically there's s degrees of freedom, and this equation will therefore, this matrix will be s by s, and it has an R square sitting here, which means that when you take the determinant, this R will have a maximum power of 2s. Now, since all coefficients of this polynomial are real, it follows from the fundamental theorem, I suppose, of algebra or some such. I don't know the proof. It's unfortunate. I'll look it up. You can claim that the values that you get, the roots that you get, I'm sorry, will either be real or they'll be complex conjugate pairs. Okay, and well, we also know from physics, which is very interesting, is that the real roots have to be negative, and the real part of the complex roots also have to be negative. Otherwise, again, the system would have an exponential increase in the energy, which is exactly the opposite of what happens in a dissipative force, which must lead to a decrease in energy. Okay, so that is what we did this time. And as usual, Kishore, if you have something to add, now is the time.
Thank you, Atul.
Okay, so it looks like Kishore has said what he always says.
Yeah.
So we also say what we always say. Have a good weekend. Actually, we don't always say that. But anyway, yeah, see you next time. Bye.
Thank you, Atul. क्या था? वो भी
Ah,
लाइव, अबे अभी भी लाइव है गधे, जल्दी जल्दी हटा.